לך או את אומרת?
לא,
היא אומרת
זה
לסבתא.
כן.
כן. לסבתא שלך?
אוקיי.
אז היא יודעת בטח. כן.
לא, אבל סבתא שלך יכול להיות? ייתכן סבתא צודקת. ייתכן שאת צודקת.
כי היא כבר הרבה שנים לא דיברה.
כן. תראי, מי?
אוי ובוי.
האמת זה נקודה באמת.
היא סיפרה שהמילה שוויצר, שזה כאילו שחצן בעברית, היא מגרמנית, אבל בגרמנית זה לא שחצן, זה להגביה.
כן?
ידעת? לא.
לא ידעתי. ואיך זה הפך להיות שחצן?
לא יודעת, אבל היא אמרה שכאילו שומעת את המילה הזאת לא פעמים במשפטים, אבל זה לא קשור, זה פשוט לא קשור. ואז...
זה סיפור רבה, אני
טוב,
חושבת.
לא, אני דברים כאלה.
כן.
איזה ממה.
זה weekend.
מושמעים.
אנחנו אומרים.
That might be a great weekend or not a great weekend. Not a great weekend? How about you?
באמת?
Rest
אולי נמצא כזה יותר חזק לעשות את זה ביותר.
semester can be over soon.
בטח שלא ניצלתי כמו שבאות, ואז זה כבר נהיה לא בסדר. זה לא ככה.
Quite a lot though. Somewhere hopefully. What do you do this summer?
לא, בן אדם לא צריך סתם לחשוב על עצמו.
אגב, מתן, איך קוראים לו?
תגיד מתן. 90% תגיד מתן.
קוראים לי?
Alright, Shavua Tov, welcome back. Alright, we're continuing along our journey. Our destination is a self-consistent theory of irregular firing. In the cortex. We have all the tools that we need, and now we're going to try to link them together and see if we can assume a certain state of the network of neurons in the cortex, in particular a state of irregular timing of the spikes, of irregular spike times, with low correlations or negligible correlations between pairs of neurons. Assume that state and then see if we can have a self-consistent picture emerge where that's an emergent phenomenon of the network itself. So we're in the midst of describing the spike trains of single neurons as Poisson spike trains, which is our assumption to begin with. Where we assume Poisson process spike train Sj for neuron J, the spikes of neuron J. And remember, for a discrete time bin Poisson process, this looks something like this. We have discrete small times bins, delta t, and then every once in a while, with random times, we have spikes. The spike train looks like this. It has a peak of 1 over delta t, and these widths delta t. So that in the limit of small delta t, we just think of this as a sum of delta functions, and we have a Poisson process with rate, say r, or potentially rj. We could have a different mean rate for individual neurons potentially, although eventually we'll just be interested in the mean, the typical average over the whole population of this. And then we also have the autocorrelation. In this case, I'll write here as the mean subtracted autocorrelation, right, between the same neuron at time t and its own spike train at t plus delta, averaged over many realizations. And for this discrete case, we know that it looks like this has the same triangle shape as the white noise. With the peak, though, is r. It's just the rate divided by delta t, and the width is delta t. So crucially, as we know, the important thing when we look at the correlation function, the really crucial thing is the area under the curve, which is just r in this case. And we know that in the limit of small delta t, so this is r and then a delta function at the time lag delta, so that when the time lag is 0, there's a spike, an infinite peak, as it were, of this autocorrelation function, and it's 0 for every other time lag, just reflecting the irregular firing of that neuron, right? So that's the assumed statistics on the whole network to begin with, and now we think about one kind of typical neuron within that network, and we know that it follows this dynamics of the linear or the leaky integrate and fire neuron. So the membrane potential Vi follows tau Vi dot equals minus Vi plus R, the input resistance, and then we're going to write as the input current, we're going to just split it into some external part, which for now, just assume that's going to be equal to for all neurons in the network, and then the input current from the whole network, which we'll write as II. Right, and that's where we're going to now put in the assumed statistics of our network of neurons all firing with Poisson spiking. Right, so what we're going to write is we have the input from the network is going to be a sum over all the other neurons in the network from j equals 1 to n, with some connectivity matrix, jij, and the spike trains, sj. So this is a function of time, right? And essentially, so this, in our assumption, we assume Poisson statistics here. We have some random variable here, and now what are the statistics per our assumption of this recurrent input current recurrent current into neuron I? So first of all, it depends a little bit on how we choose to build our connectivity matrix. Right, so we're going to assume here and throughout that this is just basically a random matrix, Jij. But in particular, we're going to set it up like this. We're going to assume that every neuron has k connections from within the network. And that those connections have some value, and all the other neurons are 0. So that means we take Jij is either some value j or 0. So it takes on the non-zero value j for k out of n randomly chosen neurons. Right, so we have random connections. We choose k neighbors from within the network. Those are going to project onto neuron I with some strength j. Notice for now I haven't scaled the strength of j with the size of the network. We're going to get to that. We're going to get to that soon. But for now, just the structure of the connectivity is either you're connected or not connected. and the projections are chosen by random. Okay? And now the crucial thing, we're going to want to know what are the spiking properties of this neuron I. So first of all, we need to know what are the statistics of this input that we've written here. Okay? Like I said in words, but I should add more formally, we said that we're also going to assume that there are not correlations between neurons, between pairs of neurons, Sj and Sk. So really independent of the time lag, we're going to assume that this is just approximately zero correlations between different neurons. And again, that's an assumption based on general empirical observations where two neurons are measured, their spike times, at least in active behavioral states where an animal is performing a task, at least in those settings, the correlations between pairs of neurons are very, very low. Okay, so these are assumptions of the individual spike trains, and then all we're doing here is we're just summing with random connectivity over a bunch of independent spike trains. So in particular, if we think about the limit of large k, right, this is going to be, we're going to assume that k is a large number. So by that assumption and the assumption of independently firing neurons, meaning uncorrelated, this whole sum is going to be in the large k limit. It's going to be a Gaussian. Central limit theorem. Right, and what I mean by that is formally is the marginal distribution of the input at some given time t is going to be a Gaussian. And then what are the statistics of that? So take the time average. And also, like I said, we're going to be interested in just the typical neuron. So I'll take the time average by the arrow brackets, just like in the exercise, and square brackets as the average over the whole population. And that way I'm kind of saying, just looking at the average neuron, what's its time averaged input from the rest of the network. Okay, and here we just have the sum. So we have this average, and then the time average, sum over Jij, the time average of Sj. So we have this sum. Now we know the sum, by construction, the sum has k terms that are non-zero. And then we have this average, and then we have the average firing rate. So, and then we have the average firing rate, and we have the value of those non-zeros. So we have k times the value of the connection for the non-zero connections, which for now we just call j, again ignoring the scaling relative to the population size that we might put in. And then just the average firing rate. Time average, population average, which we'll call R bar. So that's the mean current. It's very simple. Number of connections, strength of connections, average firing rate. That's the mean current. And then as we know, so I is Gaussian. We know it's a Gaussian process. The only thing that determines the entire statistics is the mean and then the autocorrelation function. So that's going to be the crucial statistic. So we'll write it as we've done before, the correlation of this net input now. Now we're summing over the whole network. Look at the correlation of that input with itself, sometime delta later on. So just plugging that in. Sum over j, jij, sj at time. I'll put in here as delta sj because I'm taking the mean subtracted autocorrelation. So I'll do that by subtracting the mean in here times another copy of this same current. I'll just write with a different index k just to keep things clear, but it's the same postsynaptic neuron I, so JIK delta SK at time t plus delta. Right, but as we know by both construction and assumption, these terms for j not equal to k are independent. And so, for example, they have zero correlation by construction, and so when we do the product of these sums, we're just going to get the sum over jij squared, and then we'll have the autocorrelation of the presynaptic neuron, delta sj t delta sj at t plus delta. Okay, so what do we have here for our autocorrelation? So again, we're summing over all jij, and we just have jij squared. But again, we have on average, we have exactly by construction, we have k of these are non-zero, and those take on value j squared. And the rest of them are zero. So we have k, taking over this sum of independent terms, we have k times j squared, and then just the autocorrelation, which we know has this form of our little triangle with some small width, which when we take the limit of small delta t, it has value r bar, right? The same mean rate is the area under the curve of the single autocorrelation, and then a delta function. Does that make sense? That's once we've assumed Poisson spiking of all the network, now the statistics of the net input onto a single neuron are Gaussian, and they have this mean kjr, and they have autocorrelation that's kj squared r with delta function time. Any questions to here? Yes. In the whole network, we have something like k squared. I'm assuming for each I guess I should be more explicit here. For each I take k out of the n, right? Each I has n minus 1 possible input connections. So these are j. These are the j's that are non-zero. Okay, so what do we have here? We have input that on the sum over a very large network is Gaussian, and has some mean and has a delta function autocorrelation shape. So what do we have here? We have white noise. Gaussian white noise input. There's a subtle point that I kind of mentioned at the end last week, which is the order of the limits. At some point, I take the limit where delta t is very small, and I get these delta functions on the autocorrelation of the single spikes. And then at some point, I also take the limit of large k. And so kind of what I've done here is I say I'm first taking the limit of large k. I'm kind of thinking about these spikes as actually having finite time spikes. I can think about the actual spike, which takes like a millisecond, or the synaptic current, which has a time constant of at least 2 or 3 milliseconds. So I can think about that as kind of the spike times, our finite spike times, and then I'm summing over something, and I take this limit I take the limit where this sum is over a large number of terms. So then I get a Gaussian, like I said here, I get a Gaussian as the marginal distribution of the input. And once I have that, then I just look at these statistics and conclude that I have effectively white noise input. It's a subtle point because if I would have taken the limit the other way, at least to me it's not obvious. If I first say that these are really delta functions and don't have any time widths, then to me it's not obvious that if I sum over this, I really get a Gaussian, because I still seem to get either something that's infinite at a very particular time or zero at all other times. But that's a secondary, more subtle point. The basic point here is that we can approximate a sum. If we have a large network of independently uncorrelated firing and random irregular spike times, and we sum over all of those, we get something that's at least approximated by white noise. And that is really useful to us because what we've already calculated is the neuron response. I mean, partially calculated and partially just quoted results from other people's calculations, is the neuron's response to white noise input. Okay, so let's now go back and remind ourselves of that. But essentially, we're going back to this picture. We were thinking about the single neuron responding to white noise input, but now the white noise is explicitly reflected as summing over the firing of the whole network. So now our statistics so now we have white noise input where our I bar is K, J, R, and our autocorrelation, the area under the curve of the autocorrelation, is K, J squared, R. We have this delta. So again, this term kj squared r, that's like what we wrote before as delta 0 squared tau 0, the area under the curve of the autocorrelation of the input. From both of those things, we already calculated the membrane potential response. Right, from there we calculated the membrane fluctuations, first, if we were to ignore the threshold. Right, we had sigma v squared was equal to r sigma 0 squared tau 0 over 2 tau. So in this case, we have r k j squared r bar, the firing rate, over 2 tau, the membrane potential time constant. And then we saw, in particular, what happens when sigma v is small. We saw that if the net input, if the mean input is sub-threshold and sigma v is small, then we can get something that's Poisson firing. So that's promising. So let's go back to that. Remember, we said that in the limit, in some regime where sigma v is small and our input is sub-threshold, the resulting firing rate, so now I'll write it as Ri, firing rate of this neuron that I'm looking at from within the network, although I expect it to be the same as the typical. At the end of the day, I expect the self-consistency that I wrote at the beginning means, for one thing, I need at the end of the day, the firing rate that I see at that neuron is somewhere near the average firing rate that I've assumed. That'll be the self-consistency. Right, so we said it's like the probability of spiking in a single bin of length tau divided by tau, and we argued that that's approximately equal to the integral over the tail of the Gaussian. When we look at the fluctuations of the membrane potential from its mean, we have this tail, theta the threshold minus Ri, so the distance from threshold, divided by the standard deviation of those fluctuations to infinity. and then just a Gaussian, normal Gaussian.
What's the first term, sorry?
This?
The big thing. The one about PR, is that PR?
PRS. This was what we said, the probability of a spike within a single bin of time tau. We approximate it as the tail of the Gaussian. So a normal Gaussian, a mean 0, standard deviation 1, and we're integrating from the tail, where we take the distance from threshold divided by the size of the fluctuations. Again, we assume the size of the fluctuation is something small, and that this is some positive number, so that this is already some large number, and we're integrating this tail. So now, what we could have already been a little bit more careful about is what exactly do we mean when we say sigma v is small? So from this picture, we can already get a little bit more quantitative about what we mean by that, right? Because we kind of know typical things about the tail of a Gaussian distribution, right? For example, we know that the integral within one standard deviation is something like 0.67, and the integral within two standard deviations is something like 0.97. Right, this is like your standard z-scores. So, for example, what I can do to get a quantitative estimate is think about this term here. Think about, for example, what if I think about sigma v as small, meaning like sigma v is approximately equal to 1/2 of the distance from threshold. So imagine that this mean input puts me at, like, say, for example, 10 millivolts, and I have a threshold that's something like 20 millivolts. And what if my membrane potential fluctuations have a magnitude of 5 millivolts? So if I assume that, I'm already 2 standard deviations away from the mean when I take this integral over the Gaussian, and I'm taking a one-sided integral, just one tail. So this would give us a probability of spiking within a single bin, right? It's like a 3% chance to be outside of 2 standard deviations. So it's, is that right, or is it 5%? I think it's 90%. You better remember off the top of their heads. I checked it. I think it's actually a 5% chance to be outside of 2 standard deviations, which makes you 2.5% chance to be just in one side. So the probability of spiking, 2.5% is 0.025. 0.025 probability of spiking in a single bin. And now our firing rate in that case, so let's say tau of a typical membrane potential is something like 20 milliseconds. So that makes 1 over tau. It's 1 over 20 milliseconds. And I'll multiply it by 1,000 to get to hertz. 1,000 milliseconds per second. So 1 over tau is something like 50 hertz. So if I use that, I get Ri is PR times 50, something like 1.25 hertz. Again, that was just an estimate if I was in a situation where sigma v, the magnitude of fluctuations of the membrane potential, were half the distance of the mean to threshold, right? But if I go one step further, if I take sigma v is like a third of the distance, so just a small change from instead of 5 millivolt magnitude fluctuations typically to something like 3.3, now this tail goes down from, in that case, to 99.7% within, the area under the curve within 3 standard deviations is 99.7%, meaning the probability of just being in one tail is 0.15%. So my probability of spiking goes down to 0.00015. And that would give me a firing rate, Ri, that's something like 0.075 hertz. So this we could have done last week, is just to give us a more hands-on feeling of what do we mean in this limit when sigma v is small. Because sometimes I might have written sigma v is much, much smaller than Ri or something like that. But the dependency that we found, which is what we found last week, is this exponential dependency of the firing rate on this ratio, means that really sigma v needs to be fairly close to the value of this difference between threshold and Ri for us to even fire any meaningful, to have any meaningful firing rates, right? So that's what we found. And now let's go back and take a look at what we have here for sigma v. And let's just compare, first of all, the sigma v that we've now found. We've assumed the firing in the network, this Poisson firing, independent, irregular firing of the whole network. So now let's see what we get from that. So just as a first order look at things, let's just look at sigma v divided by Ri now for this neuron embedded inside our network, right? So Ri is R times K, the number of inputs to a single neuron, times J, some value of the single synapse, times the firing rate of the network. Sigma v, the square root of what's, we have R squared here. The square root of what we have there is R, square root K, J, square root R, divided by the square root of 2 tau. Right, so R's cancel, the J's cancel, and we get 1 over the square root of 2K R tau. And so what does this tell us about the ratio? First of all, just the standard deviation of the membrane potential fluctuations relative to their mean. That ratio is going to be very small in a large network. Assuming large networks where K is at least 1,000, it can be 10,000, depending on the particular animal that we're talking about. As long as we don't have vanishingly small firing rates, then this is very small. So what does this tell us about our desire to have this self-consistent theory of irregular firing? Right? In order for this to work, so this ratio is very small. Essentially, what we're going to need to do is we're going to need to clamp this mean to very close to the threshold. That's what it seems like, at least. If we have the mean very close to the threshold, so then we can have the standard deviation sigma v be very, very much smaller than the mean, but still be large enough to give us some non-zero firing that can potentially have our desired Poisson statistics. But that's not a very promising direction to go in. because somehow we're going to need to have some kind of fine tuning, it seems like, in order to have the network firing rate be exactly such that it gives us a mean input that is very close to threshold. Any questions up to here?
So this, when talking about biological systems, this is what they mean by having an imbalance between excitation and inhibition, that leaves each cell on the verge of having an extra potential.
So that's exactly the direction we're heading in. And so we'll see exactly what we mean. So one way that we might get, maybe we can get this mean input to be right near threshold is if we also take into account the fact that we have inhibition in this network. So that's exactly what we're gonna do next. So we're going to look exactly at the interaction between excitation and inhibition, and maybe that'll help us. So now we're just going to extend the form that we wrote before and have two types of neuron, but basically we're going to, for simplicity, assume that everything about them is pretty much identical at this point. So we have excitatory neuron I that has the same dynamics that we've been studying. It's got the excitatory neuron I has its input plus some external current from outside the network. And now that input is going to be given by summing over two terms now. So we're going to sum over the excitatory network. We're going to also assume, so for simplicity, we're just going to assume that we have an inhibitory and excitatory networks. Both with N neurons and K connections per neuron. That's just for simplicity and can be very easily generalized. So the input onto neuron I from the excitatory network, JIJ EE, the connectivity matrix connecting the excitatory neuron to itself, with the firing of neuron J of the excitatory network, and then we're going to sum over the inhibitory network, JIJ EI, the connectivity matrix from the inhibitory network onto the excitatory network, times the firing, the spike train of neuron J of the inhibitory network. And we're going to have an identical thing, basically, for the inhibitory neurons. Just in that case, we have a different connectivity matrix. Then the net input onto neuron I in the inhibitory network is going to be JIJ IE. So the projections from the excitatory network onto the inhibitory network, and the firing of neuron J in the excitatory, plus the sum over JIJ II, the recurrent connections within the inhibitory network. Right, so this looks like this. We have an excitatory network, an inhibitory network. We have self-inhibition. We have inhibition from the inhibitory to the excitation. And then we have excitation, both to the inhibitory network and within the excitatory network itself. And to both of them, we have some external input as well. Okay. Now let's look at these individual elements. We're going to build them in a similar way that we did before. So we're going to, for each set of connections, so each set of connections, Jij from the excitatory network onto either the excitatory or the inhibitory, Jij AE, is going to be either some value or 0. And now I'm going to already also introduce a scaling. So now this is going to be an important point going forward, is how do we scale that strength of connection that I wrote at some point before, somewhere. So how do I think about the strength of a single synapse relative to the size of the network? So typically what we've done in the past, and what we'll start out with here, is we just say, okay, well, we want the net input to be order 1, meaning that when I take the limit, the imagined limit of the network size going to infinity, the net input should remain order 1, and so I should just scale the strength of a single synapse. I'll give it some parameter. For simplicity, I'm going to say that it doesn't depend on the postsynaptic population, so that every single excitatory synapse, whether it's internal to the excitatory network or going to the inhibitory network, has some value Je divided by K, the number of incoming synapses. Right. So this is like what we might call standard scaling. And we're going to do the same thing for the inhibitory synapses. So the inhibitory synapses, Jij from the inhibitory network onto both of the populations is going to be either Ji over K with a minus sign, so minus Ji over K, or 0. And again, taken randomly, each neuron gets K randomly chosen inhibitory projections and K randomly chosen excitatory connections. Okay, so now let's look at the statistics of the net input, for example, onto a neuron in the excitatory population. It's the same form as we saw before, just we've split it into two sums. But in terms of calculating the statistics, it's the same thing. And moreover, the way that we've defined it here, again, for simplicity, we've assumed that the connection strengths don't depend on the postsynaptic type of neuron, and that they have the same number of neurons and so on. So really, this is the mean input current onto every neuron, independent of whether it's excitatory or inhibitory. So we take this sum, again, like we saw before, we're just summing over all of these, which have K non-zero terms, times the strength of a typical synapse. So we have K times the strength of each non-zero synapse, which is Je over K, times the firing rate on average over the population, which I'll write as Re. So Re is the mean firing rate for the excitatory population. And then similarly, but just with a minus sign here, I'm going to have K times Ji over K, Ri. Right, so the net input is just Je, our parameter, scaling for the strength of the synapses, Je Re minus Ji Ri. That's the mean input. And now what about the autocorrelation? Again, that's going to drive our fluctuations. So we have delta I A at times T times delta I A at times T plus delta. And this is the same thing we saw before, but again, we just have two sums contributing this time. So again, what we would do is take the sum and write it again, but we know we've assumed independence, assuming for now that the SJs, the firing itself, are uncorrelated. We've assumed independence of the JIJs, so that when we sum, again, we're going to get Jij squared. But in this case, we just have two terms like that. Sum over Jij, and then the autocorrelation of the individual neurons. Delta Sj. This is just what we saw before. And then we're going to do that again, summing over all the inhibitory neurons. Delta Sj I at times t times delta Sj I at t plus delta. All of that, right? Again, that's the way that the fluctuations reverberate in the network. So we have randomness through the spike times and the spike firing. We sum over all that, and that gives us fluctuations in the input. Again, we have k terms that are non-zero, k times, and then for each of those non-zero terms, we take Je over k squared. And then the autocorrelation, which is Re times the delta function, the autocorrelation of a single presynaptic neuron. And then we have the same thing from the inhibitory population, k non-zero terms. Each one of those has minus Ji over k. Square that, so the minus is going to go away. And the same autocorrelation form Ri, the inhibitory firing rate, times the delta function. And so, just summing that now, we're going to have Je squared times Re plus Ji squared times Ri. All of that divided by k times a delta function. So again, this is the area under the curve of the white noise input that every neuron in this network is seeing, right? This is what we wrote before, sigma 0 squared tau 0. And again, we observed just what we saw before, that if the mean input here is order 1, the area under the curve is order 1 over k. For the standard deviations, we expect to be much smaller, much smaller than the mean. Okay. And so what we said before is that the only way this will sort of work and give us non-zero firing and maybe potentially Poisson firing is if this mean input, we also have an external term. If the mean input gives us average membrane potential, which is right near the threshold. So we have i.e. The average one over the whole population even, plus some external drive. So this must be for our theory in this case to work very close to theta. Sorry. So R times the mean current has to be very close to the threshold. We can allow for some small deviation from that, but it has to be small. It has to be on the order of the fluctuations in the membrane potential. So it has to be an order of magnitude 1 over square root of k. Right? Because the typical fluctuation of the membrane potential is the order of magnitude. It's the square root of the variance. Okay. So how can this happen? Well, let's plug in what we've got, and also by the way we've constructed this, again, where the connections are independent of the postsynaptic type. So the statistics of the input, like I wrote here, I of A for A being either I or E, so the statistics are identical. So we expect that the mean firing is actually identical. We expect Re equals Ri. And then let's just write this term again. So we have R JE times R. We'll just write R bar for the mean firing rate of the whole network. We have the mean input onto a typical neuron in this network, R times JE R minus JIR plus some external drive, which we'll also assume is the same onto both networks. And we're saying that this has to be equal to the threshold or close to it. Has to be approximately equal to the threshold. And divide by R. Remember, we have introduced this IC, which was just equal to theta divided by R, the input, the critical current that would take us to threshold. So this means that somehow we want a situation where JE minus JI times our firing rate is approximately equal to IC minus I0. Okay, so how can we do this? Well, we have this parameter I0, the external drive, so we can choose the external drive to be such, and we have these parameters JE and JI, so we can choose the right parameters. There are sets of parameters. We can choose the typical strength of a synapse to be such. We take the JE minus JI to have some value. But given that value of the strength of the synapses, that determines the external drive that we have to have, and that's the only way to keep the network operating in a stable regime where it's close to threshold, and maybe the fluctuations then can take us up and down above the threshold. Is we have to have a specific value. So fixing JE and JI determines the drive that we need. And why do I say that? Because how do I then find R? R itself, the firing rate, I want it to satisfy this equation, but remember that R itself is going to come out of here. R itself eventually is going to come out self-consistently from the picture where I have, if I'm able to make the mean input be close to threshold and have fluctuations drive it, then I get a firing rate R that's given by what we calculated last week. In this regime, it could be given by the tail of the Gaussian, right? So this is still a very fine-tuned situation where if we want the network to be able to produce Poisson firing or even really firing at all, then we need to really choose very specifically all of the parameters in the system, and it doesn't give us flexibility, so it doesn't seem to be able to do this robustly. So we'll take a break, and then we'll see how to fix this problem. כן, אני מניח שהכל כמו שהסינגל ניורון, SJ ו-SK, הם בלתי תלויים, אז גם SJ ו-SK בין הנוירונים באוכלוסיות השונות. שאלה טובה. עכשיו, אז זה נכון שבסך הכל סטטיסטיקה, אז אני נשאר בסטדי סטייט. אבל בגלל שמה שאני אחרי זה, אני כותב את הסיגנל, אז אני סוכם ומפריד בין נוירונים סינפסות מסוימות, שאותם בדיוק, זה כאילו זה מוסיף שם joint probability distribution, אז בהינתן שנוירון בזמן אחד, או סינפסה בזמן אחד, העלה או כאילו ירד, משהו חזק, אז זה כבר לא...
אז לתחום הזה כן יש שוני.
לתחום הזה יש שוני.
מהמצב הקודם.
נכון, אבל זה נכון, בסך הכל. סטייטנו עדיין בסטייטנו, נכון.
שבוע שעבר לדעתי קיבלנו את האוכל שישבנו שם כמה פגם
אני ממש הייתי פה.
התחום הזה מפריע לי את זה לשתי התפלגויות של ביחד. כשאני מגיעה לעשר, כאילו עבר לי משהו מוזר בלי שתלוי בקיום. ואז זה קצת מוזר. כי עבר לי אנחנו מבינים אותו על המצב ההתחלה. כאילו וזה גם שונה ממה שדיברנו בכיתה ואפשר לנרמל את הסיגנל. פה אנחנו רואים שהנויז הוא כאילו רק של פשוט עבר לי על שחשבנו כבר בשאלה הראשונה של המערכת. ואז זה כאילו קצת, כשאני רוצה למצוא את ה-Q אופטימלי, אז זה כאילו קצת בלתי תלוי בזה. זה תמיד זה ביטוי נורא מוזר, אני אומרת טעות אצלי ממש. כאילו כדי למצוא לזה משהו אופטימלי, כאילו יכול להיות שכנראה טעות אצלי, אבל עדיין מבחינה רעיונית, זה קצת מוזר.
אז זה נכון, שבמקרה הזה הווריאנס מה שאנחנו עובדים פה בסטדי סטייט הוא בקיו שלנו, אבל הסיגנל כן אמור אבל גם במובן של
אבל זה בעברית טוב.
זה
לא מוגדר עבור
time one, כאילו מצפים שזה אופטימלי, כן. זה אמור להיות
כאילו אני יודעת שאם אחרי
ההסתגלות שאפשר לקבל בזמן ראשון, ויש שם משהו
זה לא נכון, אבל
זה
אז אפשר רגע לשאול פשוט אני הנחתי כאילו בזמן אחד אחרי זה יש לי חצי מהמערכת במצב הזה וחצי פה ומתפלגים אחרת
אז זה לא בדיוק
כי זה לא בדיוק חצי מההתחלה
כלומר זה חצי שמקיימים את התנאי הזה וחצי מקיימים את התנאי הזה אבל הערכים אולי יש עכשיו כבר
זה כמו שהגדרנו בהתחלה הקבוע של המערכת או שזה כאילו זה תלוי בזמן או לא
המין הוא לא תלוי אבל זה אז הוא
לא, זה החל מזמן אחד
אז אפילו בזמן תחשבי אפילו בזמן הראשון בזמן הראשון
אבל לא הייתי הולכת
תראי 4 פעמים לפחות
טוב, זה האמת שאולי זה מבלבל בגלל שמה שלנו נגיד מה שלנו יש פה אי של זה מה זה? זה בהינתן מה?
זה בהינתן שבזמן הראשון היינו באחד
נכון, בזמן הראשון שכבר העלינו את החוזק של הסינפסה
לא, בזמן אפס כבר היינו באחד
בזמן התחלית, לא משנה, בזמן התחלית העלינו את החוזק עכשיו פה אנחנו על כל הנוירונים שבכלל כאילו הפאטרן מתאים לעלות את החוזק של הסינפסה אבל התחום שם, אז לא כל הסינפסות אנחנו בפועל העלינו את החוזק
ברור, זה יוצא כאילו שיש לי
נראה שזה לא מסביר
זה יוצא כאילו שיש לי איפה זה יכול להופיע כי אני אומרת עכשיו אלה שנבחנים לי ב-JJ פלוס אני כאילו אומרת שזה אנשים שנמצאים, כאילו, זה ההתפלגות שלי עבור P+, אני יכולה לראות שם, כאילו, מהנוירונים באפס, אז שליש מהם ב-M נוירונים כאילו היה לי שליש, ואז לקחת את אלו שקיבלו NJ1, אז כל מי שהיה במינוס 1 עלה ל-0.
אבל זהו, לא כל מי שהיה.
נכון, וואי, אוקיי.
זה לא רעש, זה משהו שהוא מתקן מערכת המערכת, זה לא נחשב רעש, זה בעצם התקשורת של המערכת.
נכון. מבחינת הסטטיסטיקה שלה, אז אנחנו מוצאים שהוא בדיוק יש לו את הסטטיסטיקה של white noise. עכשיו יש לו חלק שהוא דטרמיניסטי, שהוא לא ההפך, שהוא חשוב, מבחינת התקשורת חלק שיש לנו פה, כאילו המין שלו, אבל הסטטיסטיקה מגיעה כן, שגם צייני עם auto-correlation שהוא basically uncorrelated for any different time.
ממש הבנתי, אז אנחנו משתמשים במינוח הזה כדי לשים לך סטטיסטיקה. זהו, לא הבנתי.
זה מתוך הרשת הזה.
כאילו...
כאילו כזה על הכתפיים. על הכתפיים כזה. זה ממש... עכשיו זה לא לפה ולא לפה. זה לא שמפריע לך שאי אפשר לקרוא לזה קצר או ארוך? אכפת לי שצריך לקרוא לזה, אכפת לי איך נראה. אני אשך למייל, לא בטוחה שלגמרי הבנתי. נכון, יש בעיה היא ששילמתי מיליארד כסף על I ככה שילם אחד I ומיו אחד ששווים אחד מה יש כאן? יש כאן
אין מינוס הסטדי סטייט.
שאולי אני אלך לבדוק אותה. שהוא אפס, נכון? ואני לא יודעת שאולי מה שכאילו בלבל אותי בסיפור הזה זה שבסעיף הקודם אנחנו מחשבים את התוחלת של זה, אבל כשאנחנו יודעים באיזה תהליך אנחנו נעבור. ופה אנחנו רואים את זה מההתפלגות המטרופולרית. זה אומר שמה שאני צריכה לעשות זה לחשב את התוחלת פר תנאי התחלה. כאילו אני לא יודעת אם זה מסובך כי זה מסובך או מסובך כי לא הבנתי. אבל מה... וגם למה עובדת שכאילו אם זה שווה לאחד, אז זה אומר שאם התחלתי ב-1 n, אז אני נשארת במקום שלי. אמרתי שאחרי אם אני ב-x, אני גם עוברת ל-1 אז...
אבל לא בהכרח.
בהסתברויות, כאילו של קיוב אחד, כל זה צריך לקראת את החישוב הזה. לא, ואז השאלה השנייה שלי זה שזה לא בדיוק ה-n, זה n מינוס אחד, כאילו בסטפ שלי.
אוקיי, n מינוס אחד סטפ.
איך זה נהיה כל כך מאוחר בלילה? אז כל זה
אז זה קצת מסובך, כי באמת אנחנו חישבנו את זה כאילו שאנחנו יודעים שבזמן הראשון אנחנו ב-P+. עכשיו, אבל בעצם, אז כן צריך להכניס לכאן מה הסיכוי שאני אהיה ב-P+. אבל דרך טובה לחשוב על זה שכאילו שהייתי במצב של steady state, ואז מה הסיכוי שאני הולך
גם יש חבר וכאילו
ב-P+.
זה לא בדיוק חצי מהלימודים מהתואר ראשון. זה כאילו... אבל אני לא צריכה לעשות את החישוב שזה כאילו את ב' אבל עוד פעם עבור מינוס 1 חצי כאילו מה הולך להיות פה? אני התעוררתי עם מלא תפות שם ובכלל התחתנה. אני מרגישה שכזה שלחתי גם לכתוב לה.
יכול להיות
שאני חברה קרה. מה? ולא מצטרפתי חברה ממנו. ורק עוד שאלה אחת לפני שאתה מבקש באמת לחשב את התוחלת הזאת בהינתן שאנחנו מתחילים באחד מהם. זה צריך לתת משהו מכוער וכאילו לא נעים לעבוד איתו?
של מחשב זה.
כי זה כאילו צריך, זה אני צריכה למצוא, נכון?
נראה לי שאנחנו ממש לא מבינה,
וגם בחזקתי, צריך להיות שם משהו שהוא פונקציונלי. אז את זה אני צריכה לכתוב בחזקתי n, ואולי מינוס בחזקתי n כדי למצוא את התוחלת. וזה יוצא לי פיתוי, שאם אני צריכה לעבוד איתו פה, אז אני כאילו לא
בסוף למה יוצא פיתוי שהיא
זה משהו ברמה הכי אחרת.
לא צריך לחשוב את זה.
כאילו, זה כל כך מפחיד אותנו,
אבל זה אמור להיות לא כזה.
זה נורא.
כן, זה משהו שאמור להיות נוח לעבוד איתו פה.
נכון. כי עליהם הסתכלו כבר, והם עשו כבר מה לכתוב. ואמרו, הבחורה הזאת היא סתומה.
אולי הם יחשבו, אולי הם רגילים שאני בווידאו ואי אפשר לצעוק עליי, אז הוא יהיה להם כבר...
יואו, אילנה, זאת מרגיזה. אז באמת לא חווית את זה. כאילו, אנחנו מכינים אותך לטראומה, ואת צריכה להבין שזה עומד לקרות, ולהתמודד בסיפורה.
מה? לא כלום. פעם הקודמת היה
כן, היו גיבורות.
נו, אבל אני פעם ספורה, אני
את היית בארצות הברית של אמריקה, אכלת פירות טרופיים, ואנחנו היינו פה, וקיבלנו הצלחות. אז לך אין כאילו כאילו, אז לך אין בסיס לחרדה.
למה? אני מרגישה שכשלא יודעים משהו, אז הוא הרבה יותר נורא.
כן, אז אני יודעת, זה נורא. והוא הולך להיות נורא גם הבא
כן,
בשנייה.
תחשבי עליי. אולי נגרום. אולי לא נגיד. למה? אני לא בטוחה שלא.
אין לי בעיה.
זה יכול להיות גבוה מהתושוב, אבל אז אני יודע שהקטגוריה שלי יהיה פשוט.
אבל בעיקרון כן, אבל עוד לא, כן, אז אין לי שום דבר לעבוד עליו. וגם לא מתחילה וגם...
Theory should depend on what we do regular fire.
לא, אבל נראה קצת כזה, אבל בגימי...
אומייגאד, איזה יופי. אני בראש ברביעי.
סתם תבחר לה.
עד היום תכנני, יופי באמת. תכנני. וואי, הם לא ישאלו לנו שאלות, הם יגידו דברים מאוד מאוד מה יש לנו דברים. הם יתפרקו את זה.
Okay, so let's see where we're standing here. So what do we know? We're looking at the statistics of a single neuron, a typical neuron, receiving input from a whole network of neurons which we're assuming to be firing uncorrelated from one another and Poisson-like irregular firings. First crucial thing that we found really is that the typical fluctuations of the membrane potential that we expect are going to be much smaller, order of magnitude smaller than the mean input, right? Than the mean membrane potential. And so that means that if our mean input takes us either substantially below threshold, if substantially below threshold, we won't fire at all because we have this exponential dependence, right? This Taylor-Gaussian thing. If we're significantly far from threshold, our fluctuations are much smaller, so we won't fire at all. If we're above threshold, then we know that the firing we expect to see is regular firing. If we have input above threshold and small fluctuations, right, so we expect roughly to see something very similar to the constant input integrate and fire model, which has just regular spike times. So that's not consistent with what we're aiming for and what we assumed about irregular firings, right? So that's why we're looking for, okay, maybe we can have a solution which is right at threshold. But then what I said, and I kind of didn't maybe say it as clearly as possible, if we fix the parameters JE and JI, the strength of the synapses, and then say, I'm going to flip what I said a little bit, and say we have a particular external drive, I0, so then that determines the firing rate that we need that we need to get. But we have no more freedom left. We don't really have the freedom to demand that, as it were, because the firing rate, on the other hand, is going to be determined in some way by this function. This function has already the parameters put in, je, ji, and I0, and it gives us some value of the firing rate, which may or may not be equal to what we need. We need to have just something that satisfies this equation, and that's why we need fine-tuning. We're going to need to find the set of parameters that satisfy both of these equations. And we can do that. Presumably there is a solution or some number of parameters that are possible, which will give R that satisfies this side, which means we're close to threshold, and also gives us R from the response to white noise approximation of the firing rate. So that's the fine-tuning that's required, at least in this picture. And we'd like to do better than that. We'd like to be in a situation where robustly, at least for a range of parameter choices, the desired state can just emerge from that. So in order to do that, we kind of go back to the beginning. We're going to still have the same network structure, excitatory neurons, inhibitory neurons, and we're going to still, for simplicity, assume the same size for both of the networks, the same number of connections per neuron for both of the networks, and we're still also going to assume that the synaptic strength is, for now, independent of the postsynaptic type, but we're going to make one different assumption here, which is instead of the standard scaling, we're going to make a strong synapse scaling assumption. So instead of je over k, the single synapse having a scaling with the number of connections, so that the mean, say, excitatory input remains order 1 in the large k limit, we're going to instead put a scaling that has a square root of k in the denominator. So every single synapse, excitatory synapse, is je divided by square root k. Similarly, for the inhibitory synapses, every single non-zero synapse for the whole network is going to be minus ji divided by square root of k. Right? And it's strong synapses because if each one is square root of k and I sum over k such synapses, so then I have a square root of k out in front. Right? So we'll keep going with that line of thinking and conveniently just reuse what I've already written, but just change what we need to. So again, now if we look at under this scaling with strong synapses, so I look at the mean input I onto a single neuron. So I sum over of k non-zero elements, but now each one of those is je over square root of k times the firing rate of the excitatory network. And then I sum over the k non-zero terms coming from the inhibitory network, and those give me k times now ji over square root of k times the firing rate re. The sum of that is square root of k out front, and then je re minus ji ri. Okay, so this is now potentially very large. So this, on the face of it, seems like a weird thing to do. Okay. Now let's look at the autocorrelation, the fluctuations in the input. So the same way as before, if we take delta I of t and delta I t plus delta, some time lag later. Again, we're still assuming that pairs of neurons are uncorrelated, whether they're inside the same population or outside. So we get summing over these, we sum over j times j squared, and the autocorrelation of a single presynaptic neuron, and the same thing for the inhibitory population. But now, when we sum over these terms, so we have k non-zero terms in this matrix, but each one of them is JE divided by square root of K, times, again, the autocorrelation of the single presynaptic neuron, which we've seen as RE, the firing rate, times the delta function. And the same exact thing for the inhibitory population. We have K non-zero terms in the sum, minus JI divided by square root K this time, squared. So the result of that is that now the square root K is squared and cancels with K. So the fluctuations, rather than fluctuations that are much, much smaller than threshold, so we now have fluctuations that are order 1. That will turn out to really be the significance of all of this, is we've made the synapses stronger such that the fluctuations are order 1. The fluctuations now themselves are going to be in the same order of magnitude as the threshold. So maybe we can loosen this kind of fine-tuning requirement because we'll have larger fluctuations. So that's the direction we're heading, but still on the face of it, it's not clear that we've done any better, because it's true that the fluctuations are order 1, but the mean is much larger. The mean is now potentially square root of K, very, very large, and kind of feels like, well, okay, we're probably going to have to fine-tune that anyway in order to balance. Like, how do we come back to a mean that's actually not much higher than threshold or much lower than threshold, but somewhere in the range of the threshold? So it's not obvious that we've done anything useful here so far. But let's see. So first thing to do is to say, well, if this net input from within the network is going to be potentially strong, I'm going to choose to also take the external drive that I'm feeding the network to be strong. So I'll also make the external drive scale with square root of K, and then I'll just write it to have the same form, and we can think about it as also deriving from some external network where there's neurons firing with a mean firing rate R0 and have mean synapse strength that are also kind of J over square root of K. We can think about another population here, the external population, and then there also being K connections, K synapses onto every postsynaptic neuron. Or we can just think about it as a parameter, it doesn't matter, but we have now external drive that's also very strong, square root of K. And so now let's look at the total net input, kind of I bar plus I0. Again, it's the same independent of the postsynaptic. Excitatory and inhibitory neurons receive the same input for now. So just that sum net input has square root of K times JE RE minus JI RI plus J0 R0. Okay, and so again, the net input that I have onto my neuron, the net mean input onto the neuron has the square root of K term. And so, again, like I said, it seems like maybe we need fine-tuning here as well, because essentially I want this whole square root of K. It's true that my fluctuations are order 1, but if my input is much larger than threshold or much lower than threshold, then it doesn't help me. So I still need my mean input to be order of 1, because I still need the fluctuations to be able to reach threshold. So I need this whole term to be order 1, which means that I need JE RE minus JI RI plus JO R0 to be approximately 0. Right? I can have some flexibility, can be 1 over square root of K, but approximately 0, which feels at least similar to kind of the situation we had before. Now again, we're going to assume that RE is at least approximately RI. Call that R bar, the firing rate of the whole network, because it doesn't depend on the postsynaptic identity of the neurons. And then we write this is JE minus JI times R bar. And then we'll just flip the sign. JI minus JE times R bar equals J0 R0. And again, so it feels like, okay, well now again, we have to have a firing rate that is kind of predetermined by these parameters. Once we set JI and JE and J0 and R0, we're going to have this firing rate emerge. Again, we can have some small deviation from that when we're square root of k, but it's a leading order. That's going to have to happen. So are we stuck in the same bad situation where we have to fine tune the parameters? So it turns out we're not. Turns out that in this situation, we have dynamic balance. So let's call this R bar star, the desired firing rate of the network, such that this theory will work and our fluctuations will still have a role to play and will be able to give us irregular firing. So let's see what happens. First of all, we see from this equation that we should have Ji larger than Je. Which is called inhibition dominance, or is an example of inhibition dominance, is having a large enough inhibition to stabilize the internal self-excitation. Now, let's see. So this is the firing rate that we want in order for our fluctuations to be able to be meaningful. What happens if we have a firing rate that's less than that? So what if the typical firing rate in the network is smaller than R star? Okay. So what's our net input going to be? I bar plus I0, the full current population average current. So we're going to have square root of k. And then if this is smaller than what we desire over here, so then this whole term is going to be positive, right? The R that we want is the term that sets this to be right around 0. And if we have an R that's smaller than that, then this becomes square root of k and something larger than 0. So we have the whole net input is going to be square root of k in that case, right? Because we have this strong external drive and we have this inhibition dominance. So the firing, if the firing rate within the network is not large enough, we don't have enough inhibition, the external drive, which is strong, square root of k, is going to dominate. This whole term will be positive and very large. So in that case, we would be in a situation where we're way above threshold. And we would then get R that's very, very large. We would get a firing rate that's square root of k. So that's not a self-consistent possibility. If we tried to have a firing rate that was lower, we would be driven to a firing rate that's much higher. Okay, but so what if R is larger than R star? So in this case, our whole net input becomes kind of dominated by the internal firing drives mostly inhibition through that inhibition dominance, and will become larger. This contribution of this term will be larger than the external drive and negative. So this will be minus square root of k times something minus square root of k times something larger than 0. And that would drive, right, if we have now a situation where we're very far from threshold in the other direction, below threshold, so that should give us R which is equal to 0. So that's also not a self-consistent possibility. So in essence, the combination of these two features, strong external drive, it kind of forces us to have some kind of firing, and then inhibition dominance, I mean the inhibition is strong, actually force us dynamically to arrive at a situation where the only self-consistent thing that can be is for R bar, the mean firing rate in practice, to be approximately R star. And this will emerge dynamically. Right? Because if the firing rate is larger, then we have negative feedback, we have strong inhibition overall, and we're drive down below that R star. If we're below R star, then we don't have enough inhibition and we're driven way up. So the only dynamic possibility, the only stable dynamic situation is that we're actually close to R star. So in fact, we don't require fine-tuning. We just require that Ji is larger than Je, and then we have strong external drive. And this kind of fine-tuning that we want turns out to emerge dynamically from within the network. And what that looks like, if I now look and break down the separate parts of the input current that the network sees. So we have some threshold current, IC, and we have a very large externally driven current, square root of k times J0 R0. We also have a very large internally generated excitatory current, square root of k JE RE. And on top of that, the excitatory network is generating for us order 1 fluctuations around that. And then we also have a negative current, negative square root of k JI RI, and fluctuations around that. And what we're saying is once we set Ji to be larger than Je so that we have inhibition dominance, and we have this large drive, Re and Ri are going to be set dynamically such that these cancel. The sum of this and this effectively cancels the sum of that. And what we get as the net sum is going to be somewhere on the order of the threshold. This is the full thing, square root of k times Je Re minus Ji Ri plus J0 R0. The whole thing is going to be on the order of magnitude of the threshold, and the fluctuations are also going to be on that same order of magnitude. Any questions? So this is what we mean when we talk about inhibition, excitation, balance. And this is the first level of it, and it's an emergent property of the network. doesn't require fine tuning, but the excitatory current and the inhibitory current that the network itself produces will dynamically come to cancel each other out, to cancel the net current, so that the net current stays within striking range of the threshold. And then that allows those fluctuations, which otherwise would be much smaller than the mean, it allows the fluctuations to be dominant. And then it's these fluctuations that actually drive the firing. Firings are produced by the fluctuations, and therefore the firing can be irregular. So this is dynamic excitation inhibition balance, and it is the self-consistent theory of irregular firing, the only one that I know of. And there's a lot more to it, but one step more to add to it is that we can loosen the requirement, the assumptions that we had. We had these assumptions that the strength of a synapse only didn't depend on the postsynaptic, but we had all excitatory synapses have the same weight. So we can loosen that and allow for different connectivity from the excitatory population to itself as opposed to onto the inhibitory population. And then the more general setting is that we'll find a mean input onto excitatory neurons that has JEE. So now we introduce more parameters. The parameter of the synaptic strength from excitatory onto excitatory minus JEI, the typical strength of inhibitory onto excitatory, times the inhibitory firing rate, plus JE0, so also to the external drive we add another parameter, so a different strength onto excitatory and inhibitory. And similarly, for the inhibitory cells, we have a different expression for the mean current with JIE, the strength of excitatory onto inhibitory synapses, minus JII, the strength of inhibitory self-inhibition, plus JI0, R0, the strength of the external drive. So that's the more general setting, matching the picture that I drew before. And in this case, this gives us two balance equations, what's called balance equations. In the previous case where we assumed they had the same, these parameters were the same, that they reduced to a single equation. These balance equations are the equations that balance the overall net current, and so now it results in two equations, JERE, which I'll just go ahead and write it in matrix form, right? So the two equations are by requiring that both of these are order 1. And so to leading order, we divide by square root k to leading order, so we say that both of these expressions inside the parentheses should be 0. And then we can write that in the form taking a minus sign and taking the external drive to the right hand side of the equation. We can write it as a matrix, 2 by 2 matrix and vector equation, right? Because we have minus JEE times RE plus JEI times RI should be equal to JE0 R0, and minus JIE times RE plus JII times RI should be equal to JI0 R0. Again, plus some small correction term. To leading order is a set of two linear equations in two unknowns, RE and RI, the mean population rates, RE and RI. And that can be just solved very easily, invert that 2 by 2 matrix. And it turns out that also in this general case, where we have all these parameters, once we fix these parameters, all we need to have still is effectively inhibition dominance and strong excitatory external drive. And the network will dynamically reach the fixed point. It will reach the firing rates that satisfy this equation dynamically. And the requirements for that, again, so dynamic balance will emerge if we have strong enough inhibition. So in this case, right, it's not just one parameter. There's two parameters for inhibition, as it were. So right, if we look back at our picture of E and I, the network, so the overall effect of inhibition comes through two parameters. For one thing, we have the excitatory neurons that drive inhibition. So that's JIE. And we have the inhibitory neurons that inhibit the excitatory neurons. That's JEI. So both of those are kind of inhibition increasing. Those are the terms of recurrent inhibition. Recurrent inhibition can be thought of as the product of these two terms, JEI and JIE. That's the inhibitory loop. And then on the other hand, we have the excitation loop, as it were, JEE, self-excitation. And on the other hand, JII, self-inhibition, because that pushes the inhibitory neurons to be lower firing rates, which means we lessen inhibition if we increase this. So that's effectively our recurrent excitation. As a kind of rule of thumb, can be thought of as just the product of JEE, JII. And so the condition for inhibitory dominance is that the recurrent inhibition be larger than the recurrent excitation in this sense. So we need to have the product of JEI and JIE, the kind of inhibitory strengthening loop, be larger than the product of JEE and JII, the self-excitation loop. So that's one requirement. And then the other requirement is that the external drive has to overcome this inhibition dominance. So just as we saw in the case where we had fewer parameters, we needed J0, the external drive, to force us to still have firing, even though we have internally inhibition dominance. So we have one inhibition dominance, which is this requirement, and then we have two external excitatory drive has to be strong. So the external relative excitatory drive, so JE0 over JI0, that has to be, it turns out it's enough to, once we've satisfied this, then we need the JE0 over JI0 has to be larger than JEI over JII. So the ratio of the excitatory drive from outside has to be strong enough to make sure that the network just doesn't wind up silent. But that's the extent of the fine-tuning, as it were, that we need. And it's not fine-tuning at all, really, because it leaves us with an entire regime of these parameters. And once we set those parameters, then dynamically, the network itself self-adjusts. Excitatory and inhibitory networks will balance each other to satisfy these two equations. So that's our self-consistent theory of irregular firing. There's also there's a lot of work on this topic. You can ask me about it. It's been part of my research in my PhD. There's further interesting things about correlations, which here we just assumed to begin with that we had no correlations. In the end, we kind of also have to justify that, right? Because what we did, we said, let's assume that there's Poisson firing, and let's justify that in fact the firing is roughly Poisson, but it's irregular. And we've achieved that by seeing that we have these balanced equations where once those are satisfied, the fluctuations dominate and we have irregular firing. But we also assumed that there were not any correlations, and we kind of have to justify that self-consistently too. So there's a whole extension of the theory to really address that point. But that's beyond the scope here. So just to conclude, we've seen that EI balance, excitatory inhibitory balance, emerges dynamically without fine-tuning. And that's in the sense that the potentially large input currents are dynamically cancelled. And that allows fluctuations in the membrane potential to drive the firing. And yields irregular firing as an emergent property. We also see as a consequence the mean firing rates which we will observe in such a network will just be a linear function. The leading order will be a linear function of the external drive. Mean firing rates are linear in the external drive. And that's an interesting result because it actually turns out to be independent of what we assume on the level of a single neuron. Here we looked at integrate and fire neurons, but we could have changed the particular equations of what drives a spike internally within a single neuron, and we kind of still get this macroscopic balance equation emerge anyway. So that's an interesting result, is that this emerges from the theory independently of single neuron properties. So any questions about EI balance?
This whole thing falls apart if the fluctuations are not random, right? In biology, we say that these fluctuations happen in the vesicles and the synapses. Right?
So here, like mathematically, when we did this derivation, we assumed that there were fluctuations. But actually, if we build this model, we don't put in any pre-assumed randomness. So if you go to simulate these equations, you write deterministic equations for the membrane potential. You have external drive that can be just constant, no randomness involved at all. You set the parameters the only thing random is that you chose the synapses, but that's like the structural part, right? So that's not dynamic fluctuations. That's just you chose JIJs to be random. So that's just kind of the connectivity of who's connected to whom. Once you've done that, then these fluctuations are just totally emergent from a deterministic system. And I should say that there's a very strong connection to the chaotic network that Jonathan briefly talked about when we moved from Hopfield and stuff on to further. We took JIJs that were just random Gaussians, and chaos emerged from that. So there's a very, very strong connection to this situation. So essentially here you have chaotic emergent membrane potentials. But some of the continuing arguments in the literature are about, well, maybe there is biological noise which could replace the need for this kind of emergent chaos. So instead of that, you say, well, the biology actually is noisy, and the synapses themselves and the firing is not exactly deterministic, and there's all kinds of other things we don't know about. Some people would still argue, so then you don't need, and there's no need for this theory. Any questions? Okay. Alright, so that's it. I will be flying on Thursday, so I will not be here on Thursday and for a couple of weeks, but I'll be available by email, and we'll schedule a review session for something like a week before the final exam. Let me know if you want more than that or closer to the final, if you have preferences. Oh, and fill out the course survey, please. Even if you have bad things to say. Especially if you have bad things to say. אבל מה שאני עושה זה אני לוקח תחום של מי שיש לו חיובי ומסביר לזה את מי שיש לו שלילי. אז אני גורם לזה כן, בסדר, אבל אם אני יודע לבחור אותם לפי התבנית, אז כל זה יהיה חיובי. לעומת בסטדי סטייט זה שאני סוכם על אבל יש פה שאלתי אבל זה
הגדרת את
כי זה מין
לא אכפת לי גם אם עלו או לא עלו, לא אכפת לי אם הציגו להם, יכול להיות שהציגו להם זה והם לא עלו.
כן.
כי זה גם סטטיסטי אם יעלו או לא.
נכון.
יכול להיות שזה אחד והם לא עלו.
כן, אז זה...
לקחת את זה בחשבון.
כן, זה אני צריך עכשיו מחדש הולך להצטרף את זה. כאילו אפשר לקחת את כל זה בחשבון, צריך לקחת בחשבון שלא כולם, אני התכוונתי לכן לקחת בחשבון שלא כולם,
שיכול להיות שהם הציגו והם לא עלו באמת.
כן, בוודאי. להיות שאני אעשה את זה יותר קל, כי זה בעצם בא מהשאלה שהתחלתי להציג באיזה תרגול שהיו רק two states. אז שם זה באמת יותר קל, מי שלא עלה, אז יש רק הסתברות של Q או חצי Q שמלאו, או בהינתן שהראיתי פה את self 1, אז יש איזה, שגם פה זה בעצם כאילו זה הסתברות. עכשיו אני עושה תיקון שיהיה
נכון, אתה אומר גם ככה זה אפשר להתמודד.
זה גם אפשר, אם כדאי שאני אעשה את זה יותר קל. ואפשר את זה רוצים
השיעור ברמת בעצם כדי איך מחכים את הסיגנל לא על איזשהו memory pattern בזמן הראשון, אלא memory pattern שכל הזמן אם אנחנו כל שנייה, כל זמן נוסף memory pattern וצריכים לדעת כמה הסיגנל כרגע בכל ה-P memory pattern.
אבל זה כנראה לא הובהר נכון, זה אותו דבר, כאילו בתמונה הזאת אנחנו כל צעד זמן בהנחה זה הפעלת עוד memory pattern, זה השגת memory pattern כל צעד זמן. וכשאנחנו כותבים, וגם מה שיונתן עשה בשיעור, ה-F שהוא כתב, אז זה היה לפי הזמן הראשון. כל זמן אנחנו מוסיפים עוד memory pattern, עוד memory pattern, עוד memory pattern, אבל אנחנו מוסיפים את הסיגנל ביחס ל-memory pattern הראשון. מה הוא הגדיר פה? potentiated at time 0, משהו כזה. potentiated בהתחלה, כאילו בהצגה הראשונה. בהצגה הראשונה.
אוקיי, ואז הוא הגיע לזה שהפרט האקספוננציאלית, שמזניחים כלל הפשוטים לזה, ה-F הולך כמו הערך העצמי הדומיננטי, בחזקת הזמן, ו-0 לזה, אני אומר לכם, וראינו, נחשפתי, איך מזה מתחילים להגיע לזה.
אני גם חשבתי שזה הייתה חולשה בדרך של להציג את הדבר. אבל בעצם מתוך מה שאנחנו מפתחים בתוך התרגיל הזה, אז בעצם רואים את זה, כי יש לך פה איזה כאילו expectation של איזה J, בסופו של דבר אתה רואה שזה הולך כאילו מתוך פשוט ה-P, ההסתברות בזמן T. יש לך את החלק ה-steady state, ואז יש לך את הלמדה חזקת T, והווקטור שהוא הווקטור השני, הווקטור השני, לכן ב-expectation, כאילו ה-steady state נותן לך עצמי, אז ה-expectation dominated by החלק הזה, זה מה שאנחנו רוצים, כאילו, חישוב, ואז להיכנס לכאן, כאילו בידי נושא expectation מותנית, נגיד, מה שאנחנו מבקשים זה expectation מותנית שהתחלנו ממצב מסוים, נגיד אני אתן expectation מותנית על מצב כזה, אנחנו גם נקבל משהו בגנרלי חזקת T, ובעצם כל שני הסכומים האלה, זאת אומרת, אין בריבוע, בעצם ניתן לי את ה-expectation בהינתן שזה המצב, מינוס ה-expectation בהינתן שזה המצב.
מה שמציע לי במשך הזה שכאילו הסיגנל הזה לא באמת מוריד אם אנחנו זוכרים את הממורי פאטרן, אלא נשאר איזשהו וקטור.
יש טריק, כן.
זה לא תנאי מספיק,
נכון, זה תנאי מוכח.
עוד שאלה קטנה, אמרת שהמכפלה הזאת מודדת
מחזק את זה, אז זה אומר שהאינהיביטורים, אז זה מחזק את האינהיביציה. אם אני מחזק את זה, אז גם דרך עושה את האספקט סך הכל אינהיביטורי של האינהיביטורים, הופך אותה, כי הם מפעילים יותר את האינהיביציה. זה מחזיק אחד מהם או שניהם, סך הכל מחזק את האינהיביציה. זה אומר כן, כאילו בביולוגיה זה ככה, 99.משהו% מהזמן שנוירונים מסוימים, אז ההשפעה שלהם על כל נוירון שהם שולחים אליו היא אינהיביטורית, שלהוריד את המתח בנוירון. נוירונים אחרים אינהיביטוריים, כך שכל הנוירונים שהם שולחים אליו, ההשפעה תהיה חיובית. אז זה מצטרף ה-J.I.J, שכאילו ה-J.I.J של נוירון J יהיה או חיובי לכל I או שלילי לכל I. ואז אנחנו כאילו מצאים כל המטריצה, אז יש פה את האינהיביטורים, תמיד, אז כל זה יהיה חיובי, J.E.E, I.J, אז פה J.I.J, I.E, גם, אז זה החיובי וזה החיובי, ופה זה שלילי, זה J.E.I, זה יהיה מסובך, אז איך אנחנו מחשבים את ה-R יוצא משוואות כאלה, בסופו של דבר פה על ה-R, ה-R אנחנו יכולים לעשות את rate, זה דבר כזה.
רק רגע, תגיד, C, פתרתי את זה, ראיתי שעשיתי את זה לא נכון, זה רק לצד אחד וסינפסה אחד, ואני לא מבין איך לסכום פה, איך להתחשב במרקוב, כאילו במטריצות האלה, לכל אחת מהמטריצות, ולבצע את הסכום הזה על כל הצעדים שיש. לא, כאילו, איך אני סוכם מטריסיס של הסתברויות בעצם, אני אעשה את זה כאן.
שני דברים בנפרד, קודם כל אתה סוכם מהסינפסות שונות. ההנחה פה שהסינפסות בלי תשביות אחד מהשני. ולכן כשאתה סוכם על הרבה כאלה, מה קורה?
זה TLT, כאילו אני משתמש בגאוסיאן.
כן, ופה אפילו כאילו אתה אפילו TLT עוד לפני זה, כאילו the weak sense law of large numbers, פשוט סוכם על n בריבוע, והממוצע לא אפס, אז תחליף בממוצע.
איך אני חושב את הממוצע או את השונות של כל אחד מאלה, כי אני יכול, זה לא בעיה לעשות את הסכום, אבל לחשב את הממוצע והשונות של כל אחד מאלה לכל אחד מהצעדים, זה מה חשוב.
אבל קודם כל אתה יכול להזניח את השונות. באסנשל לא מציעים פה, אתה פשוט יכול להזניח
את הממוצע. את הממוצע, אבל לפי צעדים.
אוקיי, אז עכשיו שאלה שנייה לפי צעדים.